Hello, I am N.Kripa, Assistant Professor, Department of Biomedical Engineering from Bharat Institute of Higher Education and Research, Chennai 73. We are going to see about the course Biosensors and Measurements. And the topic we are going to discuss is signal conditioning and processing in measuring instruments. Signal conditioning and processing is very important in biomedical instrumentations because the signals which we are acquiring through the sensors from the body is very low, and also it has more noises because of the patient movement and due to external environmental conditions. So because of that, each of the signals has to be amplified and the noises has to be reduced, and then further signal conditioning has to be done in order to know the results and the output. So here we are going to see about the basic instrumentation equipments which we are using regularly. So in that, how the signal is being conditioned and processed, we are going to see. Signal conditioning. So analog signals require some form of preparation before they can be digitized. Signal conditioning is the manipulation of a signal in a way that prepares it for the next stage of processing. Signal processing. Signal processing is an electrical engineering subfield that focuses on analyzing, modifying, and synthesizing signals such as sound, images, and scientific measurements. So, in these categories, the first and simple basic equipment which we are going to see today is voltmeter, that is digital voltmeter. Voltmeter is an electrical measuring instrument used to measure potential difference between 2 points. The voltage can be measured maybe either AC or DC. Two types of voltmeters are available for the purpose of voltage measurement, that is analog and digital. Analog voltmeters generally contains a dial with a needle moving over a recording to the measured and hence display the value of the same. With time, this analog voltmeter are replaced by digital voltmeter due to the same advantage associated with the digital systems. Although digital do not fully replace this analog voltmeter, still there are many places where analog voltmeters are preferred over digital voltmeters. Digital voltmeters display the value of AC or DC voltage which is being measured directly as discrete numerical instead of a pointer deflection on a continuous scale as an analog instrument. Now coming to the working principle of digital voltmeter, this is the basic block diagram of digital voltmeter. Here we have AND, pulse generator, input signal, and decimal or digital display. So the block diagram is a simple digital voltmeter. So we have input signals. It is basically the signal that is the voltage which is to be measured. The next is pulse generator. Actually, it is the voltage source. It uses digital, analog, or both techniques to generate a rectangular pulse. The width and frequency of the rectangular pulse is controlled by the digital circuitry inside the generator, while amplitude and rise and fall time is controlled by the analog circuitry. AND gate. It gives high output only when both the inputs are high. When a train pulse is fed it along with the rectangular pulse, it provides us an output having train pulses with duration as same as the rectangular pulse from the pulse generator. So this decimal display, it consists the number of impulses and hence the duration and display value of the voltage on LED or LCD display after calibrating it. Now coming to the working of digital voltmeter, unknown voltage signal is fed to the pulse generator, which generates a pulse whose width is proportional to the input signal. Output of pulse generator is fed to one leg of the AND gate. The input signal to the other leg of the AND gate is a train of pulses. So the output of AND gate is positive triggered train of duration, same as the width of the pulse generated by the pulse generator. The positive triggered train is fed to the inverter, which converts it into a negative triggered train. Output of the inverter is fed to a counter, which counts the number of triggers in the duration, which is proportional to the input signal, that is voltage, which is under measurement. Thus, counter can be calibrated to indicate voltage in volts directly. Now, there are number of types of uh, digital voltmeter based on the analog to digital conversion methods. Some of them are ramp type digital voltmeter, integrating type voltmeter, potentiometric type digital voltmeter, successive approximation type digital voltmeter, and continuous balance type digital voltmeter. Now coming to the advantages which is associated with the digital voltmeter, readout of DVMs, that is digital voltmeter, is as easy. It eliminates observational errors in measurement committed by operation. Error on account of parallax and approximation is entirely eliminated. Reading can be taken very fast. The output can be fed to memory devices for storage and further comparison. It is versatile and also very accurate. It is very compact and it is also very cheap. It has low power consumption or requirements and its portability is very increased. Nowadays, digital voltmeter are also replaced by digital millimeters due to multitasking features, that is, it can be used for measuring current, voltage and resistance. But there are some fields where separate digital voltmeter are being used. Now the next topic is digital multiplier. Digital multiplier or DMM is a test equipment used for resistance, voltage, current measurement and other electrical parameters as per requirement and displaying the results in the mathematical digits from an LCD or LED readout. It is a type of multimeter which functions digitally. In digital multimeter, we can incorporate many types of meters like ohm meter, ammeter, voltmeter for measurement of electrical parameters. So the first is digital voltmeter, that is DVM. Digital voltmeter is the basic instrument which is used for measurement of voltages through the use of analog to digital converter. The basic principle behind the digital multimeter is the analog to digital converter because without this we are not able to convert the analog output into digital form. It comprises of comparators, encoders and digital display. The second is digital ammeter, DAM. Digital ammeter uses a shunt resistor to produce a calibrated voltage which is proportional to the current flowing. To read the current, we must first convert the current to be measured using a voltage by using the known resistance. The developed voltage is calibrated to read the input current. The third is digital ohm meter, DOM. A digital ohm meter is used to measure electrical resistance which obstructs the path to the flow of current. Now coming to the working principle of this multiplier, this is the basic block diagram which has the input signal, analog to digital converter, a display unit and digital converter. So as shown in the block diagram, a typical digital multiplier, the input signal that is AC or DC voltage, current, resistance, temperature or any other parameters is converted to DC voltage within the range of the analog to digital converter. So the analog to digital converter then converts the pre-scaled DC voltage into its equivalent digital numbers, which will be displayed on the display unit. Sometimes digital converter block is implemented with the microcontroller or microprocessor manages the flow of information within the instrument. This block will coordinate all the internal functions as well as transferring information to external devices such as printers or personal computers. Now coming to the parts of DMM and its functions. The first one is display unit. The LCD screen present on the upper portion of the multiplier basically displays 4 or more digits and also shows negative value if necessary. A few or today's multimeter have illuminated the display for better viewing in low light situations. The second is selection dial. It allows the user to set the multiplier to read different electrical parameters such as multi-amp, MA of current, voltage, resistance, capacitance, etc. We can easily turn the dial anywhere for specific parameter measurement. The third is ports. Two ports are available for the front of every multimeter, except in some 4 ports are available for measuring current in MA or A. COM stands for common and is almost connected to ground or considered as the negative connection of a circuit. We generally insert the black color probe into COM port. MAV ohm port allows the measurement of current, voltage and resistance or considers as positive connection of a circuit. We generally insert the red color probe into MAV ohm port. Next is red lead. It is connected to voltage, resistance or ampere port, considered as positive connection of a circuit. The last is black lead, connected to common or ground port, considered as negative connection of a circuit. Now coming to the advantages and features of digital multiplier. It has light in weight. It is capable of giving more accurate readings. It measures a lot of physical quantities like voltage, current, resistance, frequency, etc. It is less costly, it is very cheap, and it measures different electrical parameters at high frequencies with the help of special probes. The next instrument we are going to see is the Cathode Ray Oscilloscope, CRO. Cathode Ray Oscilloscope is a very useful and versatile laboratory instrument used for display measurement and analysis waveform and other phenomena in electronic circuits. CROs are in fact very fast XY plotters displaying an input signal versus another signal versus time. Cathode ray oscilloscope quantities operate in voltage. However, it is possible to convert current, strain, acceleration, pressure, and other physical quantities into voltages with the help of transducers and thus to present visual representation of a wide variety of dynamic phenomena on CROs. Cathode ray oscilloscope are used to investigate waveforms, transient phenomena, and other time-varying quantities from a very low frequency range to the radio frequencies. So they are now available which can measure frequency up to 1 gigahertz and observer events as a small 20 hertz in duration. Now coming to the construction of cathode ray oscilloscope. So this is the basic structure which is being seen inside of the CRO. Please refer the diagram which I have given here. So the cathode ray oscilloscope consists of a cathode ray tube which is the heart of the tube and some additional circuitry to operate the CRT. The main parts of a CRT are: the first is electron gun assembly, second is deflection plate assembly, third is fluorescent screen, fourth is glass envelope, and fifth is base. We will see one by one all these parts. The first is like electron gun assembly. So in cathode ray oscilloscope, this is the part from which the electrons are born initially. It produces a sharply focused beam of electrons which are accelerated to high velocity. This focused beam of electron strikes the fluorescent screen with sufficient energy to cause a luminous spot on the screen. After leaving the electron gun, the electron beam passes through two pairs of electrostatic deflection plates. The source of the focused and accelerated beam is the electron gun, which emits electrons and forms them into a beam consist of a heater, cathode, a grid, a pre-accelerating anode, a focusing anode, and accelerating anode. So the electron passes through a small hole in the control grid. This control grid is usually a nickel cylinder. So the grid with its negative bias controls the number of electrons emitted from the cathode and hence the intensity is controlled by the grid. The electron emitted from the cathode and passing through the hole in the control grid are accelerated by the high positive potential which is applied to the pre-accelerating and accelerating anodes. The second part is deflection plate assembly. Electron beam after leaving the electron gun passes through the two pairs of deflection plates. One pair of plate is mounted horizontally and produces an electric field in the vertical plane. This place produces a vertical deflection and is called vertical deflection plate or Y plate. The other pair of plane is mounted vertically and produces a horizontal deflection. This pair of plates is called horizontal deflection plates or X plates. Plates are flared so as to allow the beam to pass through them without striking the plates. The third heading is fluorescent screen. The front of the CRT is called the face plate. It is flat for screen size up to 100 mm into 100 mm and it's slightly curved for larger displays. Face plate is formed by pressing molten glass in a mold and then annealing it. So the inside surface of the face plate is coated with phosphor. Activator in current use the metals such as silver, manganese, copper, and chromium. So when an electron beam strikes phosphor crystals, it raises their energy level. This is called cathodoluminescence. Light is emitted during the phosphor excitation and this is called fluorescence. So when the electron beam is switched off, the phosphor crystals returns to their initial state and releases a quantum of light energy. This is called phosphorescence or persistence. In bombarding electrons, the solution, when it strikes the screen, releases secondary electrons. The secondary electrons are collected by aqueous solution of graphite called aquadag, which is connected to the second anode. The collection of the secondary electron is necessary to keep the CRT screen in a state of electrical equilibrium. And the next is glass envelope. The working part of the CRT are enclosed in an evacuated glass envelope so that the limited electrons are able to move freely from one end of the tube to another end. And the last heading is base. Through this base, connections are made to various parts from cathode ray oscilloscope. Pins come out of the base and external connections are made. Now, some of the applications and the uses of CRO are voltage measurement. It measures the current measurement, examination of waveform, and measurement of phase and frequency. And some of the uses of CRO are: it is used in laboratory. The CRO can be used as display unit for different types of waveforms. It can measure short time interval. In voltmeter, it can measure potential differences. Now the next is cathode ray tube, CRT. The cathode ray tube is a display screen which produces images in the form of video signals. It is the type of vacuum tube which displays images when the electron beam through electron guns or strikes on the phosphorescent surface. In other words, CRT generates the beam, accelerates it at high velocity and deflects it, creating the images on the phosphorus screen so that the beam becomes visible. Now coming to the construction and working of CRT. The CRT consists of electron gun assembly, electrostatic deflection plate, screen for CRT, and aquadag. The electron gun assembly, deflection plate assembly, fluorescent screen, glass envelope, based on the important parts of the CRT. So, the electron gun is the source of electron beam. The electron gun has a heater, cathode, grid, pre-accelerating anode, focusing anode, and accelerating anode. The electrons are emitted from the highly emitting cathode. The cathode is cylindrical in shape, and the end of it, the layer of the strontium and barium oxide is deposited, which emits the high emission of electrons at the end of the tube. The electron passes through the electron in the small grid. This control grid is made up of nickel material with a certainly centrally located hole which is coaxial with the CRT axis. The electron which is emitted across the accelerating anodes. The beam is focused on focusing anode. The accelerating and focusing anodes are cylindrical in shape, which has a small opening in the center of each anode. After exiting the focusing anode, the beam passes through the vertical and horizontal deflecting plates. Next heading is electrostatic deflection plate. The deflection plate produces the uniform electrostatic field only in one direction. The electron beam entering the deflection plate will accelerate only in one direction, and hence the electron will not move in other direction. Next, the third topic is screen for CRT. The front of the CRT is called the face plate. The face plate of the CRT is made up of entirely fiber optics which has spatial characteristics. The internal surface of the face plate is coated with the phosphor. Then the phosphorus converts the electrical energy into light energy. The energy level of this phosphorus crystal raises when the electron beam strikes on it. This phenomenon is called cathodoluminescence. The light which is emitted through this phosphor creation is excitation is called as fluorescence. When the electron beams stop, the phosphor crystal regain their original portion and release a quantum of light energy, which is called phosphorescence or persistence. And the last one is aquadag. The aquadag is the aqueous solution of graphite which is connected to the secondary of the anode. The aquadag collects the secondary emitted electron which are necessary to keeping the CRT screen in the state of electrical equilibrium. The next is the working of digital storage, the working of cathode ray oscilloscope. So the working of cathode ray tube detects on the movement of electron beam. The electron gun generates sharply focused electrons which are accelerated at high voltage. And after exiting from the electron gun, the beam passes through the pair of electrostatic deflection plate, and these plates deflect the beam when the voltage applied across it. The one pair of plate moves the beam upward and the second part of the plate moves the beam from one side to another. The horizontal and vertical movement of the electron are independent of each other, and hence the electron beam positioned anywhere on the screen. The working part of the CRT is already been discussed, which has the electron gun assembly, the screen for CRT, aquadat, etc. Now coming to the digital storage oscilloscope. The digital storage oscilloscope is defined as the oscilloscope which stores and analyzes the signal digitally, that is, in the form of 1 or 0, preferably storing them as analog signals. The digital oscilloscope takes an input signal, store them, and then display it on the screen. The digital oscilloscope has advanced features of storage, triggering, and measurement. Also, it displays the signal visually as well as numerically. Now coming to the circuit and principle of digital oscilloscope, it has amplifier, digitizer, memory, analog circuitry, waveform connection, CRT, then it has trigger or clock, time-based, horizontal amplifier. The digital oscilloscope digitizes and stores the input signal. This can be done by the use of CRT, that is cathode ray oscilloscope, and digital memory. The block diagram of this basic digital oscilloscope is being shown in the below. You can refer it. The digitization can be done by taking the sample input signal at a periodic waveform. The input signal is digitized and stored in memory of the digital form. In this state, it is capable of being analyzed to produce a variety of different informations. So to view the display on the CRT, the data memory is again constructed in analog form. So here are some modes and factors which has been used here. Roll mode, store mode, hold or save mode. So the input signal is applied to the amplifier and attenuator section. The oscilloscope uses some type of amplifier and activation circuitry as used in the conventional oscilloscope. The attenuated signal is then applied to the digital amplifier. To digitize the analog signal, analog to digital converter is used. The output of the vertical amplifier is applied to the analog to digital converter section. The successive approximation type of analog to digital converter is mostly often used in digital storage oscilloscope. The sample rate and memory size are selected depending upon the duration and waveform to be recorded. So once the input signal is being sampled, what happens? The analog to digital converter digitizes it. The signal is then captured in the memory. Once it is being stored, the memory, many manipulators are possible as the memory can be read out without being erased. So this is the waveform reconstruction of digital storage oscilloscope. For visualizing the final wave, the oscilloscope used the technique of interpolarization. The interpolarization is the process of creating the new data points with the help of known variable data points. The linear interpolation and sinusoidal interpolation are two processes of connecting the points together. In interpolation, the lines are used for connecting the dot together. Linear interpolation is also used for creating the pulsed or square waveform. For sine waveform, the sinusoidal interpolation is utilized in the oscilloscope. Now coming to the advantages of this DSO, it is easier to operate and has more capabilities, and the storage time is infinite. The display flexibility is available. Number of traces that can be stored and recalled depends upon the size of the memory. The cursor measurement is possible. The characters can be displayed on screen along with the waveform, which can indicate waveform information such as minimum, maximum, frequency, amplitude, etc. The XY plots, BH curve, PV diagrams can also be displayed. So keeping the records is possible by transmitting the data to the computer system where the further processing is possible. The signal processing is possible, which includes translating the raw data into finished information, that is, computing parameters of a captured signal like the RMS value, energy stored, etc. So these are all some of the basic instruments where the signals which are being taken are being processed and computerized. Thank you.